In example 9, we're going to perform the integration on the function of x squared e power x. In order to perform these integrations, we have to apply the integration by part formula not once, but twice. Let's see how we do it. As we mentioned in the previous examples, there are two choices for you to identify the u and v function. The integration by parts formula requires us to cast the integrations into the form of u dv equals to uv minus v du. The first step you have to do is to identify which terms in the integrand that you will call u and which term you want to call it dv. Here there are two choices. Either you call u to replace x squared and ex dx to be replaced by dv, or you can identify u to be ex while dv to be identified as x squared dx. So which one should you choose? One criteria to make your choice is by looking at the dv term. When you integrate the dv term, you get the expressions of v. And here, when you integrate it, you get n term of e power x. If you integrate the differential of dv, you get v, which ends up x power 3 over 3. Here, you compare the expressions of v. It increased the powers in x from power 2 to power 3. However, in this case, when you integrate the dv, the exponents remains the same. Before integrate over v, the exponents is e power x, and after integrations, v remains e power x. Here you can see that integrating the variable v by choosing dv to be e power x ex does not increase the power in v, whereas if you choose dv to be x squared dx, you increase the power of v to power 3. Therefore, you should choose dv to be e power x dx, so that the resultant values of the variable v after integration does not increase in the power. We should be choosing the u to represent x squared and dv to represent e power x dx. You integrate over dv to obtain the expressions of v, which is e power x, with a constant 0. You take the differential of u, you get 2x dx. So you substitute the expression of du, u, dv, v from the writing here into the integration. Here, the integration is u dv equals uv minus v du. So we just have to substitute in the expression of u, v, and v du to the right hand side of the equation, which reads u as x squared v e power x minus integrations of the expression v, which is e power x times du 2x dx. So you end up to be an expression of x squared e power x minus 2 times x e power x dx. Now we have expressed the integrations of x squared e power x into the forms x squared e power x minus 2 times another integrations of the form x times ex. So it is obvious that we have not finished with the integration. We have to further perform these integrations using another round of integration by parts, which has been discussed in the previous example. So here I'm not going to call this u and v, but I'm going to call this p dq to distinguish it from the previous integrations. I would write these integrations of x e power x into the forms of p dq, pq minus q dp. And I have to then make a choice for the p and dq. So according to the previous criteria, the choice of p has to be x, dq made to be ex dx, so that when you integrate with respect to q, you get an expression of ex which does not increase in the power. You take the dp, which is just simply equals to dx. Then you write down the integration to be the product of p, q, where p is x q is ex, minus integrations of q, which is ex, and dp, which is dx, x times e power x minus e power x plus n constant. So this would be the answer for the integrations of this. Here I rewrite the original integrations to be like what you see here, and we just fill up the integration of x e power x. That is the solution to the integrations of x squared e power x. In conclusion to this video, we have shown that in order to perform integration for the integrand x squared e power x, we first apply integration by parts by choosing dv to be e power x dx and u to be x squared. By this choice, we end up to a result of x squared e power x minus 2 times another integration. The applications of integration by parts for the first time reduce the integrations that involve x squared down to the integration that involve only x. So we can see the reduction in the complexity of the integrand. The integration has to be solved further for this integral by applying another round of integration, which is quite straightforward, where we choose the x as a function p, ex dx as dq, and we perform the integration by parts for this expression to arrive at this. With the expressions of this, then the integrations of the original integrand is solved.